Hello guys, today I'm going to talk about work that was put on the archive last year. It is titled as Generalizable Long Horizon Manipulations with Large Language Models. In this work, the authors introduce a framework that utilizes the large language models to generate primitive task conditions for each subtask in a long horizon manipulation. And then these task conditions are combined with a low-level trajectory generation and adjustment. This framework can accelerate the long horizon manipulations and to deal with novel objects and unseen tasks. Let's first look at the overall framework in Figure 1. Clearly, this framework consists of two components. The higher level component is to prompt a large language model to generate the language task conditions for each subtask in a long horizon manipulation tasks. And then these tasks are combined with the demonstration data for the robot arm to generate and adjust the low-level trajectories. Let's look at the core concept in this work, that is the task condition definition. The task condition consists of 5 aspects. The first is a language task name, and then the large language model need to define the relevant objects. After that, the preconditions need to be given with the large language models. The preconditions are the environment conditions that must be satisfied before the execution. Otherwise, it would lead to task failure. And the post conditions are the environment conditions that mark the success of a primitive task. And the last aspect is the valid collisions during the task execution. Let's look at the listing 1, the example given by the authors. When we need to define the task condition for the task move bottle into the box. So the relevant objects are the bottle, the box, and the gripper. The preconditions need to satisfy before the execution are the gripper grasping the bottle and the box is open. After that, the post conditions are the bottle inside the box, the gripper inside the box, the gripper grasping the bottle, and the box is open. The last component is the collisions. The valid collisions that can happen during the execution. That is the touch between the gripper and the bottle. Any other collisions are invalid. So after defining the task conditions, we need to determine that whether the task condition is satisfied with the current frame generated from the RGBD cameras. In this work, they use the semantic point cloud generated by the RGBD cameras to obtain the environment information that are essential to determine whether these task conditions are satisfied. So this environment information includes the object center position and the bounding box of each object. It can be obtained with the semantic point cloud. And then the spatial relations can be determined by with the bounding box for each object. In this work, they define 4 spatial relations between the object and between the objects. The spatial relations represent the relationships between two objects. For example, the bottle inside the box, the gripper inside the box. In this work, there are overall 4 spatial relations that are the inside, above, below, and in front of. And after determining the spatial relations, we also need to obtain the object states. The object states describe the states of a single object. And in this work, they focus on the gripper is grasping or not grasping. The container is open or closed. The gripper state can be obtained with the bounding box for each object, and the container states can be obtained from the simulators. Last is the collisions happen during the execution, and it is obtained with an implemented function in the simulator. You can look in detail in this paper about how they prompt the large language model to generate the spatial relations, the collision generation, and the object states with a chain of thoughts prompt. So after getting the task conditions generated by the large language models, we want to know how to combine these task conditions for the with the low-level trajectory generation. The low-level trajectory learning is conducted with an imitation learning method named dynamic movement primitives. It is an effective algorithm that can be learned with the locally weighted regression method. In this work, the authors proposed 2 algorithms to combine the task conditions with the low-level trajectory generation and adjustment. Let's first look at the first algorithm to determine the which preconditions is satisfied for the current frame. So the algorithm first determine whether the preconditions for the current task is satisfied for the current frame. If it is not satisfied, then another primitive task that is aiming to satisfy the current preconditions is utilized to replace the current task. And again, the preconditions for the current task need to be determined whether the conditions is satisfied or are satisfied or not. It is an iterative algorithm. For example, when the precondition gripper grasping bottle is not satisfied, then it will lead to grasp the bottle as a new primitive task, and its preconditions will be generated and satisfied recursively. Okay, then after determining the current satisfied preconditions and the current valid primitive task, the goal positions and the task collisions are used to determine the goal positions for the current trajectory generation. And during the execution, if there is an unexpected collisions during the task execution, then they will stop the executing and go backward 10 trajectory points. And then they update the goal positions regarding where the collision happens and adjust the rest of the trajectories with the new goal positions. Okay, let's look at the simulation parts. So as we mentioned before, there are two components in this framework, the task condition generation and the low-level manipulation execution. So let's first look at the performance achieved by the large language model regarding generating and generalization of the task condition. As shown in Table 2, the task conditions generated by the large language model is pretty accurate for these primitive tasks, and it can have a comparable results with the conditions generated from the environment ground truth. And then after combining the task conditions with the low-level trajectory generation, the success rate is shown in Table 3. As shown in Table 3, they combined image-based imitation learning baseline with the DMP algorithm and their algorithm with the conditions. Apparently, the DMP algorithm provide a stable baseline for the algorithm, and it can improve the success rate with a large margin, even without the conditions generated by the large language models. And their algorithm, their framework with the task conditions generated by the large language model, and for the trajectory generation and adjustment, the success rate for each primitive task can also be improved further. Okay, and let's look at the generalization performance of their proposed framework in long horizon tasks. As shown in Table 4, for some long horizon task, when combine the conditions from the large language model or from the ground truth from the environment, the performance, the success rate can be improved by a large margin. And when it faces the novel objects or novel primitive tasks, these traditional algorithms without the large language model fails to generalize. However, their method utilizing the generalization ability of the large language model to generalize to novel objects and novel primitive tasks with some success rate. They also conduct real-world experiment, and they conduct a long horizon manipulation task in their framework, in their simulators. However, they do not open source the simulated platform, so it is hard to validate their proposed method in their simulators. Okay, let's again conclude the paper. First, we can tell from the paper that the large language model can generate reliable task conditions for these primitive tasks. And then these task conditions is helpful for the low-level trajectory generation in a long horizon manipulation task. However, in their work, some conditions like the object states of the containers, the collisions need to be obtained from the simulators. And maybe we can obtain from the semantic point cloud or from the RGB inputs with the foundation models like in the future. That's all. Thank you.